presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day so far. I want to welcome you on down to the stream. My name is Dan, but you could just call me, Dan or Daniel, or Dr. Page, whichever you'd prefer. I'm not too terribly picky about that. You could call me Hey You, whatever. I hope you're having a wonderful day so far. Let me know in the chat how you're doing today. Let me get the chat open just for a little bit before we get into things here today. I am feeling a bit better than I was on Thursday. Thursday I was a little sick. That's actually why we didn't have our live stream on Thursday. And I couldn't have a chance to get it on the weekend either because I had to go to do a couple of family related matters. So this week we will have our live stream right now. Sorry, I'm getting really excited here. Then we're going to have our live stream again on Thursday. I thought to make up for last week, I'm going to play 2 games on Thursday as opposed to just one. So I'll probably play some more Link's Awakening DX on the Game Boy Color. But I also have something else in mind too. So we'll see what that's all about. It should be a lot of fun. But anyway, just a few things before we get started. If you find yourself curious about getting the notes for today's lesson, they'll be available on patreon.com/pagewizard. So just check out the links in the description. And of course, check those out. Of course, tell your friends to come and subscribe and follow. And of course, be sure to hang out in the chat. I take questions in the chat. I have the chat just sitting out over here with me. Depending on which platform you're on, I can even hear your comments. So keep in mind that regardless if you can see the chat or not on the screen, it's still available to me. And of course, I'm happy to answer or take any questions. It doesn't necessarily have to do with what we're talking about. Now, another detail is, so if you want the notes for today's subject, it'll be posted later today. And in addition to this, if you want to find a way to get that otherwise, the lesson today is adapted from my notes in this book called Advanced Data Structures, an Introduction to Data Structures and Algorithms. This is available on Amazon and also on Google Play. So you could get that there. But if you want the notes specifically for today's lesson, check it out on Patreon. It'll be available over there. Let me just put this over here. So anyways, what's the plan for today? So depending on how much time we have, so for sure I'm covering what we call the single source shortest path problem. We'll talk about some properties that problem has. In addition to this, we'll also talk about what is called Dijkstra's Algorithm. It's a classic in combinatorial optimization. And after that, if we have a little time after that, I may cover Prim's algorithm again. Now, if not, I think it'll be fine enough just covering what I've just already outlined. I think these are pretty fundamental things, and I want to make sure I take some good, delicate care with it. We're going to have ourselves a great time here today. Other than that, just as I mentioned before, if you enjoy what you see, make sure you follow, subscribe, and of course, tell your friends to come on out. A lot of people just don't know that this is what happens here. So just keep in mind that, of course, any little bit of support helps. So it's always where things begin. And of course, that's how it always is. And I just do what I do here. So please just consider supporting the work here. It's a lot of hard work goes into every one of these lessons. Okay. So other than that, just want to outline a couple of other things just quickly. So I mentioned this the other week as I am working on a mailing list. So I'm going to try to make that available. I'm hoping for the next big announcement I have before we get into our lesson is I'm hoping to have this mailing list available because the website is currently still under construction. and I'm planning to try to make it so that there's courses available through the website, and I'm going to try to make it so you can support me directly through that website as well. In addition to this, so I want to try to get this mailing list together so that way you could enroll in that, and I'll try to make update emails that I could send out maybe once a month or once or twice each month. That just basically show what the lessons are from each month. And of course, if you're ever curious, by the way, what's coming up for events, just go to pagewizardgames.com/schedule. And you could find out all of the events that are planned or what is going to be coming down the pipeline that is currently established is coming out, okay? So if, for example, you want to know what the topic is for next week, either just bug me or, of course, you could just check that out. But the next big announcement I have before we get into our lesson here today is that next week I'll be doing a Halloween lecture. So yeah, I know, November 1st. Yeah, the Halloween lecture is the day after Halloween. So in that lecture, I'll be covering ways to escape a haunted house that has traps in it, which should be a lot of fun. So it'll be a variant of what is called the Canadian Traveler problem. It's a version of an online shortest path problem. That's why I really wanted to focus on today's lessons, because knowing about this algorithm is going to help you understand what's coming up for the Halloween special, okay? So it's not required for the lesson, but most certainly if you want to know how to algorithmically do one of the subroutines for the algorithms in that lesson, it'll be in today's lesson, okay? So anyways, let's get started, okay? So let's get going here. So before we get into anything, I need to define what problem we're going to be studying here. What we're going to do is I'm going to lay out a bunch of terminology first, and then we're going to get into some properties that this problem has, and then I'll define it formally for you within the prism of one of these formalizations, okay? So today we're going to talk about the single source shortest path problem. Today we're going to talk about the single source shortest path problem. So I need to define a few key things for our problem here. So we're going to let G be a weighted undirected connected graph with non-negative edge weights. So that just means that those numbers that we have on the edges that could represent, say, for example, the travel distance from one vertex to another. Just as an example, you can think of it just as costs too, or just as I'm going to call them, weights. That it has to be that they are 0 or greater. They can't be negative in the conception here. It's going to be an important detail for us. So I'm going to presume I'm given one of these types of graphs. So one other thing is that the graph is also simple. So that's just always a presumption I make. Otherwise, I would call it a multigraph, just to be clear. So suppose I'm given a path. So that's just it's going to be given as, suppose I give you a path P, and this would just be a sequence of adjacent vertices. I'm going to give it as a set of edges in the order for which you would encounter them. So V0, V1, V1, V2. It's the same information. If I didn't have any edges, it means it didn't go anywhere, right? So I have V1. So it goes from V0, V1, V2, all the way up to the VK minus 1 to VK. So this is what my path would look like in terms of the edges. So I'm going to define what is called the length or total weight or cost. Or total length or cost or total, we'll say total weight. Wait, I was getting a little excited here. The total length, the length or total weight or cost of a path is the sum of the weights of edges in P, which I'll denote more formally like this. I'll call it the weight of that path, or the total cost, or the length. So I'll denote it like this, which formally it looks like this. The sum from I is equal to 0 to k, from where I take the weight of each one of the edges, and I'm just going to add them up. So we're going to be studying what we call the single source shortest path problem. And to do this, I'm going to need a little bit of terminology here. So let's get into this. So the first thing I need to make sure you are aware of is what is called the shortest ST path. So imagine I give you two vertices. It's going to be simply a path P. So some path P from S to T with minimum length. Right? That's what that means. So the first thing I really want to point out before we get into any examples is I really want to hammer in what a shortest ST path exactly is from a theoretical standpoint. So there's a very important property. In fact, there's going to be two properties that we would like to have at our disposal in regard to this problem. But before I define what this problem is, which the intuition is really simple, right? I have this graph. I would like to find the shortest ST path. So if I have some way of formalizing this, there's several ways you can do this. I'm going to formalize it a specific way later. I would like to have some property for these so-called shortest ST paths. So there's going to be two properties that we're going to use here. So there's going to be a couple useful properties. So a couple useful properties. So I'm getting really excited here. So the first one that we're going to discuss here is that if I give you a shortest ST path, I can actually decompose that shortest ST path into some set of subpaths, right, that are just like connected together like this. I could take those and so that I can end up with the shortest path. So each one of these little pieces of the shortest path are also shortest paths. So let me rephrase this a little bit more carefully. So what I'm saying is a subpath, so that's just a part of a path. A subpath of a shortest path is also a shortest path. So that's the first one. Now, you shouldn't let me get away with just saying this without anything in discussion. Now, I normally, when I teach this, I will either give you a proof for this or I give you the explanation for this. So the proof for this is rather nice and straightforward. So because we have the time, I'm going to prove it for you here today. So let's consider the following lemma. So this is going to be a key ingredient later for when we prove the correctness of an algorithm that solves this so-called single source shortest path problem. So here's a lemma. So suppose we are given shortest ST path. So suppose we're given a shortest ST path, P, And it has the same kind of form we just talked about. V0, V1, V1, V2, all the way up to VK minus 1, VK in G, as we've already defined earlier, where I'm going to assume that S, where S is equal to V0 and T is equal to VK. So now what we're going to do is we're going to consider a subpath. So let's consider a subpath. Consider a subpath. So consider a subpath P prime of P, where P prime looks like this. It's going to start at some vertex Vi. And it's going to go all the way up to, actually, let me add another edge in here just to make it clear what we're talking about. It's going to be Vi plus 1, Vi plus 2. And it's going to go up to and include, as the last edge, Vj minus 1 Vj. And it's going to be the case that 0 is less than or equal to I, is less than or equal to j, is less than or equal to k. So this is going to be somewhere along our shortest ST path. So I'm going to pluck off, I'm going to have I and j. They could maybe at the start, it may be towards the end. The point is it's somewhere in that path, P. It's one subpath in the larger path. So just to make this actually a little easier for us, I'm just going to give this a somewhat different name. Instead of calling it P prime, just to emphasize the point I'm getting at, I'm going to call it Pij, like this. I'm doing this deliberately, by the way. I just really want you to really understand that sometimes it's helpful for us to have special names for these variables. So subpath Pij is a shortest Vi Vj path of G. That's the lemma. So that's what we're going to prove here, is that Pij, this subpath, is in fact also a shortest path. It is a shortest Vi Vj path. So you might say, Dan, how are we going to go about this? So I want to kind of give you the game plan that I have in my head. And this is a nice technique that you can use in a lot of different contradiction proofs, specifically around those where a problem exhibits something called optimal substructure. That means that within a given optimal solution, you can find optimal solutions that you could decompose from it. So in this case, for example, I have a shortest path. I'm going to show you that, yeah, you could take a part of this path, one contiguous part of the path, that also has to be a shortest path. So I got to show you now how we can use that information to prove, in the form of a contradiction proof, how I can establish the truth of this, that it holds. So where do we usually start with a contradiction proof? I'm going to assume, so remember, this is the claim, that subpath Pij is a shortest Vi Vj path, right? So to assume otherwise means what? It means that it's not, right? So we're going to assume that Pij is not a shortest Vi Vj path of G, right? That's a good place to start to set up a contradiction proof. But what does that mean? What does it mean as a result? There has to be another Vi Vj path, right? And it has to be shorter. That's what it means. Then there exists another VI, VJ path, and I'm going to call this one P prime IJ. This is why I'm going to give this a nice name here. P prime IJ in G such that the length of P prime IJ is strictly less than the length of Pij. In plain language, this is just means that we have a shorter path. So let me draw you a fun picture of how we can use this to help us yield a contradiction. So let me just get rid of this board over here. So what we're going to do is we're going to take advantage of a technique that very often is called cut and paste. So if I have a shorter path, what can I do with that information? Let me draw you just a picture just to give you a flavor for what we're talking about here. So remember, I have this path P. It starts at S. And it eventually reaches VI. Keep in mind, VI could be S, but the point is it's somewhere along this pathway. This is VJ, and we eventually get the T. Keep in mind, VJ could be T, for example. But this right here, all of this is Pij, right? That's what that is. However, in our setup here, we presume that there's another path. There's another path. VI, VJ. So it goes from VI to VJ. Now, I don't know exactly what's going on in here. It's just stuff, right? There could be some traversal through to get from VI to VJ, some path. And this other path is going to be shorter. Do you see how I made it a little shorter? I just made it a little shorter. It could be any way shorter. This here is P prime IJ. Now, what I'm going to do is I'm going to use the fact that I have a shorter path from VI to VJ to build a shorter ST path. Do you see how we can do it? Do you see how we can do this? Well, let me just start us off, okay? So we already have this VI and VJ here. So I was going to suggest that we construct a new ST path, P prime. So this is why I wanted P prime. By taking P and doing something to it. Do you see how I can make a shorter path from S to T, presuming that this is a shorter path than this one? Well, what can I do? I can just simply take this, put this here. You see I have this right here? I'm just going to put this path right there. And that's P prime. So P prime is just going to be the path from S to VI that I had up here. So I'm just going to take that part, put that there. I'm going to take this path from VJ to T. I'm just going to take that part. I'm just going to put that here. And then I'm just going to replace. So I'm just going to replace this guy with this. And I get P prime. So I'm just going to simply take P and replace, I'll say replacing subpath Pij with P prime Ij. But what does that mean if I measure the length of this path versus this path? Well, this one is strictly shorter than this one. So that means that the overall path that I just constructed has to be shorter, right? Then the length of P prime is strictly less than the length of P. But what does that mean? What does that mean? Can that happen? Is this possible? What is P? P is the shortest ST path. So can P prime exist? No, it can't. It can't. Which is not possible. Which is not possible as P is a shortest ST path. So that means that we simultaneously have that P, as a result of this, is a shortest ST path, but it also isn't at the same time. That is a contradiction. That's a contradiction. That concludes the proof. So it means that if I give you a shortest ST path, that means that I can take two arbitrary vertices in that path, and if I look at the subpath, that also has to be a shortest path. So this is a rather valuable detail for us, because that means that if I give you a shortest path from one vertex to another, to extend it to another vertex that is adjacent to one of the ends of this path is simply to, in a sense, extend it via some edge, or via an edge, to be a bit more precise. I'm just making up words here now. So that brings me to the second property here. So there is a tree, particularly if the graph is connected, it's a spanning tree. A tree of shortest paths from a source or start vertex. Start vertex S to every other vertex. To every other vertex of G. So what we call this is a shortest path tree. So this is called a shortest path tree of or from S. So you might ask, Dan, what does this mean? Well, let me give you an example just so you can get an idea of what we're talking about here. So let's do an example here. So suppose I give you the following graph. I'm going to make it a little bigger of an example. So let's consider this graph as an example. I'm going to put some edge weights on these. I must stress again that these edge weights are non-negative. So they're not allowed to make them negative numbers. This is an important detail as I'm going to discuss eventually. So I'm going to have that have edge weight 8, 3, 2, 2, 2, 5, 2, 2, 6, 2, 3, 1, 6. There we go. We have all of them we have edge weights. I'm going to presume that this vertex here is S, and this other one over here is going to be T. So suppose I want to find a shortest ST path. Now, I want to first, before anything, I want to show you and convince you that there exists a shortest path tree in this graph. So let's talk a little bit about this. So what's the shortest path from S to this vertex? Well, it's just simply, it uses this edge, right? But how'd you know that? Well, among all the vertices, you go from S to that vertex. Notice that, how do I know that there isn't like another edge just hiding somewhere else that's going to get me there shorter? Well, how do I know? Well, because all the other edges were either the same or bigger, right? So one thing that's really important to notice about the fact that the edge weights are non-negative is that whenever you travel from where you're starting to another vertex, you either are staying put or you're moving in some direction. So like, for example, I move a little forward, right? I move forward by 1 in this example. So let's keep going here. So notice here that to get to this vertex, the shortest route of this is just to go from S across this edge. And you might say, Dan, well, how do you know the other ones? Well, let's think about this. Okay, so notice that if and keep in mind, I will ask you to check this carefully with yourself here, but you can keep going through this process. And I must stress that I'm only just doing an example right now. I'm not going through a specific process with you. I'm just going through and showing you what one of these shortest path trees would look like. Do you notice that once I'm over here, notice that it's 2, 2, and 6. Notice that any way I could have gotten to this vertex, it's going to require me to use more than 3 units to get there, right? So it's 6 versus, well, it's technically 7. It's, here would be 8. Here it's 6. Either way, it's going to be more. So let's take this route with the 3 here. And then lastly, we just got 3 here, and we got 2 here. I think we got all the vertices, right? So this example here, this is an example of a shortest path tree of S. So notice that if I want the shortest ST path, notice it's just one of these paths in this tree, right? So notice I just go like that. And that's how I can get the path from S to T. So I could, in the same vein, I could start at T and work my way parent by parent, or what we call by its predecessor. So I could go for the predecessor of T to this vertex. The predecessor of this one is S. So I can work my way backwards or forwards depending on how I formalize the tree. But the key thing I want you to notice is that if I look at any pair of vertices, that the pathway in this tree, remember there's only one unique path. That's a property a tree has, is that there's a unique path between any 2 vertices, right? So I pick any 2 vertices. It is the shortest path from S to that vertex. So actually, I should be a bit more precise. I said any two. I should be specific, because that actually isn't going to be true. It's always from S to each of the other vertices, right? So what I described to you before that would be the shortest path from any pair of vertices, right? It would be the shortest among any pair. Here we have a specific pairing. It is S versus another vertex in the graph. So you might ask, Dan, what does that mean overall for us then? So I called S a source vertex, and notice that I have a single source, S. I would like to find the shortest S other vertex path. That is an example of a path from the source to any other vertex in the graph. This is characterized by the shortest path tree of S, or from S. And if computing this tree is solving the single source shortest path problem. So the single source shortest path problem is actually computing this tree. So you might ask, Dan, how do I know this exists? So I'm going to show you how we can build one of these trees. So the big thing I really want you to know about this tree is that every path from S to another vertex T in the tree is a shortest path. But the key thing here is that we have the source vertex. We're not computing all possible pairs of shortest paths. We just want all the shortest paths from this source vertex. And naturally, the former, what I just described to you, is what we call the all pairs shortest path problem. The latter is the single source shortest path problem. So if we wanted to find the shortest ST path in a graph, so if I want to know how the shortest way to go from point A to point B, it's going to be in this tree. So, and you can see, based on some of the previous lessons we've had, how you can compute specifically one of those paths once you have this tree, okay? So that's what the single source shortest path problem is. So let's describe that now. So I would like to be able to compute one of these things under our setup. So what's the single source shortest path problem? Is compute a shortest path tree. Compute a shortest path tree from S. So S is called the source or start vertex to every other vertex. So that's the goal here. So I'm going to show you how you actually build one of these trees, okay? See, so one other detail I really wanted to point out to you, and you may not have caught on to this carefully, is that it doesn't matter for this tree if the path is simple or not. So if you were to just presume I'm trying to compute a simple path, it doesn't matter here. That distinction doesn't matter here. So notice that if you didn't have a simple path, you'd just be repeating edges or vertices, right? Which would simply mean that you're just wasting time, right? So I must stress that the shortest path tree, that this path that you get is a simple path. So that's just something I wanted to mention for you. So if you find yourself wanting to compute a shortest ST path that is simple, this is also capable of doing that. Pretty interesting stuff, right? And I must stress, remember, this is because of the setup we have for our problem, is that the graph has non-negative edge weights in it. So if that isn't true, we can't necessarily guarantee that the simple versus not distinction is the case. Furthermore, you can't necessarily guarantee that this tree exists. So what we're going to do now is we're going to see how we can actually construct one of these shortest path trees. So are there any questions or anything of the kind? Don't be shy. Happy to answer any questions. This marker is being a little funky, so I'm going to just put it off to the side and I'll look at it later. I won't throw this one. This one might be one we can forgive. Oh. So now we got the setup for what we're going to talk. The main subject of today is going to be Dijkstra's algorithm. So what we're going to be going into next is we're going to be using the machinery that we've talked about here to see how we can actually construct one of these shortest path trees. Now, one other detail I also want to point out to you is I've defined the problem with respect to undirected graphs. Dijkstra's algorithm also works with directed graphs, just to be very clear. So this characterization with the non-negative edge weights, this is also true there. However, the characterization when you have directed graphs is specific. It'll be something I'll bring up towards the end of our lesson here today. But the one thing I want to point out is that if you have this in place for directed graphs, there's a really nasty way to create graphs where there is no such, it's ambiguous if there even is one of these shortest path trees. It just doesn't exist. Because there could exist a shortest path that doesn't take the form like this. Instead, it actually takes the form that it has to be that the shortest paths form a cycle if the path is simple. But if it isn't simple, there isn't actually a shortest path tree. So we're going to see that a little later on, okay, everybody? So what I'm going to do next is I'm going to erase the boards. And then we're going to talk about the so-called Dijkstra's algorithm. So we're going to have a couple key ingredients, and we'll talk about how we use those to come up with Dijkstra's algorithm. And then we're going to, after that, we're going to establish the correctness of Dijkstra's algorithm. So just remember, the big thing is that if ever I want to compute a shortest ST path, T could be any one of the vertices in this graph, and you pick a source. So if ever you wanted, for example, to compute the shortest ST path, again, but you change what S is, you're going to have to recompute this tree possibly. Or you're going to use the information from the tree to recompute a new shortest path tree. But I'm not going to focus so much on that here. But the point is that you're going to have to redo the work you have here. But you might ask, Dan, why are we computing this whole tree when I just want the path? The thing is that for the algorithm, it doesn't make any difference. You just may as well just compute this tree. But if you don't need the whole tree, you're welcome to augment the algorithm so that you only are just getting that ST path. But you're going to find that this is a rather natural characterization if you ever want to, say, use this tree for all sorts of different applications. So, for example, suppose that this is like your where you want to make sure whenever you're sending off messages, say in a network, I want to make sure that they go from the shortest, I always compute them from I always want to use routes that cause the least amount of work to transmit it from one to the next to the next. So I want to have it where the length or cost to get from this one to any other vertex is as little as possible. So such a tree is capable of doing this. So, for example, if you think about this as a literal network, and you imagine these are costs to transmit information from this one to that one, or this one to over there, it's going to hop from vertex to vertex. And I would like to minimize the cost to transmit from that one to that other vertex. This is one way you might characterize that. This is one of the reasons why I'm showing it to you like this as well. It's rather quiet here today. But that's okay. That's okay. So I'm just going to erase the board here. So one thing I will mention while I'm erasing the board is that in the previous live lesson, I talked about Prim's algorithm. You're going to find that I'm going to bring up Prim's algorithm quite a bit in this discussion. Why? Because it uses the algorithm I'm going to present to you uses very similar mechanisms. It's not the exact same algorithm, and I must stress the shortest path tree isn't a minimum spanning tree. Just to be very clear, they're not the same thing. But they have a very similar structure to them that allows me to develop an algorithm that's going to be quite similar to it. Okay, so let me just get a different marker out. This is a red one. Let's just want to make sure I got a pretty decent one here. See, this one's, I don't know, I don't trust that one. I got a lot of markers around here. Question is, which one can I trust? Okay, let's just go with this one. Let's roll with this one. Okay, so now let's move on to talking about what Dijkstra's algorithm is. So next we're going to talk about what Dijkstra's algorithm is. So previously we talked about what the single source shortest path problem is. Now we're going to talk about an algorithm for computing shortest ST paths. Specifically, to solve the single source shortest path problem, it is to compute a shortest path tree of the source S. This marker's giving me a little bit of a hard time. It's gone. It's gone. It's out of here. Okay. So next, I just want to mention a couple of quick things. So first, if you're wondering why it's called Dijkstra's algorithm, this is named after the computer science pioneer Dijkstra, who developed this in the late 1950s. So before we get into the nitty-gritty of this thing, I thought I would give you a couple of motivating ideas for how we're going to come up with this algorithm. So there's kind of two ideas. So there's two ideas that we've previously seen before that I want to bring together. So the first one is that for unweighted graphs, we know how to compute shortest paths, right? Because remember, that's just a special case of our problem. If I wanted to compute a shortest path tree, it would just be one where the edge weights are all the exact same. And in that case, I could use breadth first search, right? So we know how to compute shortest path trees on unweighted graphs using breadth first search. So we know how to do that, right? Likewise, previously we've also seen how we can compute minimum spanning trees. That had also a mechanism for producing a spanning tree. The shortest path tree is a spanning tree, just to be very clear, because our graph is connected. So there's going to be an element of Prim's algorithm that we've seen earlier. We're going to try to generalize that concept so that instead of it being about trying to compute the least weight cost of the spanning tree, I want to make it so it's as small as possible. Instead, I'm going to change it. I'm going to change it or augment it or generalize it, whichever one is your pleasure. I'm going to make it so that instead of it being about measuring the total cost over the entire graph, meaning that it's just the least weight edge, right? That's what I did with Prim's algorithm. Instead, I'm going to make it so it keeps track of how far away from the source we are. So we're going to take an idea. So I'm going to say perhaps let's take an idea from how we computed MSTs, so minimum spanning trees, to account for distance from S, the source. So this is going to be something we're going to call an edge relaxation. So you're going to look at this and be like, that reminds me a lot of the thing you do in Prim's algorithm, except we're instead going to account for not just like the cost, the weight of that edge. Now I want to take into account the distance I am for my vertex from S. I would like to keep track of the shortest distance so far. Let's think of it as an estimate if you would prefer. So that's going to be the purpose of what we call an edge relaxation. So we're going to keep track of a so far shortest distance from S to each vertex V. We're going to call that V dot D. Now you might recall I used the same name for when I talk about Prim's algorithm. It's going to have the exact same setup that I did in Prim's algorithm, except it's going to be that it's going to keep track of the so far shortest distance, not the cost of the least weight edge that we use, as I mentioned. This is going to translate very naturally into a very simple modification to from what we had for Prim's algorithm. So consider an edge. So consider an edge E, where it's going to have its endpoints being U and V. Where U is the vertex. Is the vertex that most recently joins the blob. Joins the blob B. And V is not in the blob. So to update the distance is to relax the edge. So to update the distance, what you do is you relax the edge UV. So that's what we'll refer to it as. So if we find a shorter distance, we relax the edge as follows. So it must satisfy the following condition. So I'll remind you a little bit of something. So if U dot D plus the weight from U to V, so this edge, is less than currently the best distance we have for vertex V from S, then we're going to relax the edge. So relaxing the edge is simply where we update D for V, such that it's just going to be U dot D plus the weight of this new edge that I've encountered. So that's what an edge relaxation is. if you're not sure about what we're looking at here, just keep in mind this is just like the one we've seen in prim, just now we're taking into account the distance from S to this vertex V. I want to see, do I currently have the shortest distance to V from S? So to do this, I have to account for the distance that I took to get there. So what is this all going to translate into? So now I know how to compute a spanning tree using Prim's algorithm. What I could do is try to adapt this idea of an edge relaxation as follows. So do you remember that I told you when we computed a minimum spanning tree, what happened was we had a blob and it would start at some vertex. In our setting, it's going to be S, the source. And this blob is always going to, it's attempting to devour the entire graph. So it goes vertex to vertex, picking some edge. In the case of Prim's algorithm, it always picks the least weight edge from inside the blob to outside the blob, and then it extends off to that next vertex and devours that vertex, making the blob larger, so growing the blob. And at the end of this process, what's inside the blob is a minimum spanning tree in that case. What happens here in contrast is I have a blob, but it's not just a blob that's going to follow that kind of rule. So as I mentioned previously, Prim's algorithm is a greedy algorithm. It always picks the least weight. It's always going to use a least weight edge to get to the closest vertex that's outside the blob, allowing it to grow, right? So it's always going to find the one that's outside the blob, but it goes from inside the blob to outside the blob via a least weight edge to accomplish this, to grow itself. And it finishes when the whole blob, well, the blob has devoured the entire graph, right? The same idea is going to be here, except it's even simpler. The blob is lazy. This blob is lazy this time around. As opposed to in Prim, it's just going to gobble up whatever's closest to the blob. That's a very proactive blob. The one we're going to be considering this time is a very lazy blob. This blob is going to be lazy. It's going to, imagine it starts off at vertex S at the source. And what it's going to do is it's always going to pick the vertex that is closest to the source. So that means that this blob is really, really lazy. So what it's going to imagine is you're going to imagine this blob is going to be sitting here being like getting bigger and bigger as it devours parts of the graph. And what's going to happen is you're going to imagine this blob is sitting there. And you imagine each one of our vertices is hanging almost away from the blob. And the blob is always going to find the one that's closest to its, we can imagine the source is where its mouth is, if it had a mouth. Yeah, don't get too imaginative with this. And what it does is it pulls in to the source, the next vertex that is closest to it. So it brings it in. Whichever one is the closest is the next one closest to the blob's mouth, right? So it's going to get closer and closer, and it will grab whichever one is the closest. So unlike in Prim's algorithm where the blob just goes for the one that's closest to the blob, it's just going to go for the one that's always closest to its mouth at the source. It's a lazy blob. It doesn't want to just travel to the one that's closest to the entirety of the blob. It requires it to be the one that's closest to its mouth, okay? And that's going to be the idea behind Dijkstra's algorithm. So again, it is a greedy algorithm, just like Prim's algorithm was. But here's the idea. The blob in Dijkstra's algorithm. Now, if you don't like me talking about it as a blob, it's just a set of vertices. So these are the ones that are going to be leaving the priority queue that we had in Prim's. The blob in Dijkstra's algorithm always devours next the closest vertex to the blob's origin. To the blob's origin. So let me reiterate. So in Dijkstra's algorithm, our blob is always going to devour the next, it's always going to get the one that's the next closest to the blob's origin, which is the source. So now that we have all these bits and pieces, let's put Dijkstra's algorithm together. And here's the catch. Here's the catch. It's just going to look like I wrote down Prim's algorithm, where instead of having it where we have the updates of the least weight edges, as we had before, we've just changed this one bit about how the blob picks the next closest vertex. It always picks the one that's literally closest to the source. So it has to go from inside the blob to outside the blob again, but it's always going to be picking a vertex that is closest to the source, the origin of the blob, where its mouth is. So, let's write out Dijkstra's algorithm now. So we've got our algorithm. So we're going to call it Dijkstra. It's going to have the graph G, and it's going to be given the source S. So it's input. It's going to be a connected, undirected, weighted graph. G is equal to VE, and a vertex or source, however you'd like to call it, S, which is going to be one of the vertices. And as output, now I'm not going to return anything in our version of Dijkstra here, but you can easily make it so it returns all sorts of different things. I'm just going to make it so it constructs the shortest path tree. So it's going to produce the shortest paths from S to all vertices. So this is the shortest path tree rooted at S, right? So I promised you I was going to show you how you actually construct this, and this algorithm is what we're going to use to say that. So you're going to see that the setup for this is just like Prim's algorithm. I showed you how to represent prims using a priority queue. You're going to use the same setup. So you're going to first do some little bit of prep on the graph. So you're going to assign each one of the D values for each vertex to be not 0, it's infinity, right? Because we haven't yet encountered all of them yet. We have to, and the blob has to find them first. And then each one of its parents or predecessors are going to be null. We haven't found them yet either. So we start off by assigning the D value of the source to be 0, right? Because it's the shortest distance. The distance from S to itself is 0, right? There's nothing too mind-blowing about that. Then next, we're going to make the priority queue. We're going to call it Q. It's going to contain all the vertices. All vertices V in V, where V dot D, where each V dot D is the key of an entry, right? So this is something we've established earlier with Prim's algorithm. We're going to have it where the D values are going to be the keys that we're going to use to maintain the priority queue in our heap-based implementation here. Because remember, we always want to get the one with the smallest D value. That's true regardless of Prim or Dijkstra's algorithm. So it's always the one with the smallest D value. We're just updating the D value a little different here. So now we just have our loop. We're just going to go through and keep repeatedly taking out vertices and giving them over to the blob to devour them, or the vertex joins the blob. While Q is not empty, we're going to do the following. We're going to pick out U min, which is going to be the one that is closest to the blob's mouth next. We're going to go remove min. We're going to apply remove min on the priority queue. We're going to pull U min into the blob. Because remember, as we do this, every single time, it's going to leave the priority queue. We're never going to put vertices back into the priority queue. We're going to potentially update their keys, but most certainly we're not going to put them back in once they get out. So each one's going to get their turn. That's something to keep in mind. So upon doing this, you can mark each one of them. I'm not going to include that line, but you most certainly could put it in there optionally if you want to make sure each one of the vertices gets marked. It's not required at this stage because we could ensure that we're never going to put back U min. U min's not going back in. But for each, we have to go through the incident edges. For each edge, U min V. So we're going to go through all the incident edges on U min. We're going to potentially have to do an edge relaxation. Well, specifically, we're going to have to relax some edges potentially. So if U min dot D plus the weight of U min V is strictly less than V dot D, what am I supposed to do then? I relax the edge. Then I'm going to update V dot D to be U min dot D plus the weight of the edge to get to V from U min. Now, remember, this is where we're going to update the key by decreasing it, because we found a shorter way to get to V from S. We're going to decrease the key for V. It's going to be decreased down to V dot D because I just updated it. And I'm going to update the predecessor or parent in the shortest path tree. V dot parent is going to be updated to U min. That closes this. That closes the loop. And then we'll close the while loop. So we go lose our for loop, while loop, and that's Dijkstra. That's Dijkstra's algorithm right there. Pretty fascinating stuff, right? So you might ask, Dan, what is the time complexity of Dijkstra? Now, there's the short answer and then there's the long answer. The long answer is that you just have to go look back at how we did things with Prim's algorithm. Because do you see that there's anything different other than we just changed a few lines in here, right? We just changed how remember, the edge relaxation is like a generalization where we focus on the distances, right? Everything else about the algorithm is exactly the same as Prim's. But you notice that all these changes, they don't affect the overall time complexity, right? So the time complexity is the exact same as we had from Prim's. So just to be clear, we established earlier that if I use an adjacency list, and a binary heap, we could show that this algorithm runs in big O of m log n as G is connected. Note that you can easily pick up the other representation of Prim's algorithm, do the same little twit, and you can end up with big O of n squared for the time complexity in that situation. Likewise, again, if you want to update or upgrade your priority queue so that the heap being used is instead of Fibonacci heap, you can improve the overall time complexity again, like we had before. So that's Dijkstra's algorithm. Pretty fascinating stuff. Let's do an example just to make sure we're clear about it. So let's do an example. So after that, we'll focus in on the correctness of Dijkstra's algorithm. So let's do an example, just so we can see how this works. So I'm just going to erase the board, then we're going to move back the pseudocode, so that way we can easily understand what's happening here. So I'm just going to draw our graph, and we're going to go step by step through it, okay? So let's head back over here. Let's keep going. Let's keep going. Push it on over. There we go. That way we got the whole algorithm here, and we also got our example here. So this is going to be our example. So this is our example. So I'm going to have 5 vertices. 1, 2, 3, 4, and 5. I'm going to make the source vertex be 4, just to be clear. And then we're going to have our d values for all of these. So remember, they all initially start off as infinity and null, respectively. So d is infinity, parents null. I'll get out of the way in a moment. So there's our graph. We're going to be doing this when the source is 4. So we're going to produce a shortest path tree of 4. I'm just going to fix that 3. The 3 is a little weird. There we go. So let's compute the shortest path tree of 4. So the first thing, if you look at our algorithm, the first thing it does is we set up all of these as we did here. Then it assigns s.d to be 0. So 4's d value becomes 0. So vertex 4 now has a d value of 0. I guess I should draw some edge weights, so let's do that. We're going to kind of need those. 1, 2, 3, 3, 1, and 4. There we go. So anyways, we have our example. And when we initially set it up, when s is 4, we make the d value, as we have right here, 0. And now remember, all the vertices are in this priority queue. So it pulls out the first vertex with the smallest d value. In this case, that would be s, right? That would be s. So it means that 4 comes out of the priority queue. But what does that mean? It means our friend the blob devours this vertex, right? That's where it starts off. So the blob says, hey, I'm going to eat this, and its orifice is going to be right here, okay? So it's going to be at 4. So remember, 4 is s. So remember, we're always going to find the vertex that is closest to s that's outside the blob. And that's what it's going to devour next. So we've done that. Now we got to go through all of our incident edges on 4. So we got to check this edge and this edge. So we see that, hey, look, if I take 0 plus the weight of this edge, which is 1, that is less than infinity. So I can update this. So I'm going to relax on this edge. So this is 1. And the parent needs to be updated. It's updated to 4. Same thing here. I found a shorter way to get the vertex 3 via this edge. And that's all my incident edges. So that finishes up dealing with vertex 4. So far, are we doing okay? Now next, the blob is going to find the next closest vertex to the blob's mouth. Remember, it's really lazy. It's going to drag that vertex, the one with the smallest d value, to its mouth and devour it, okay? So it's just, I'm just going to sit here. You're going to bring the one that's closest to me by my mouth. You're going to bring that to me. So in that case, it would be vertex 1, right? So how do I know which one is an edge that's going to be the one that would be the one that I extend from vertex 4 to vertex 1? So which edge do I add in to the shortest path tree? It's this one, right? It's always umin and then its predecessor, right? So immediately once you've removed umin, you know which edge goes into this shortest path tree. It's right here. So if you had an auxiliary data structure where you wanted to add them in explicitly, you do it right here before this loop. So now the blob will devour vertex 1. And we go through all the incident edges on vertex 1. So notice here that I have a 3. So notice that the distance from S to 2 would be, in this case, 1 plus 3, because remember, that's what the d value is here, giving me a 4. And the parent, in this case, would be 1, right? Because that's the predecessor. That's how I would get to 2. Now notice that I have a distance of 2 here versus a distance of 1 plus 3, which is larger than 2, so we wouldn't relax this edge. We relaxed on this edge, but not this one. Do you see that? Notice that because this was the one with the smallest d value at that time, notice that I wouldn't relax this edge again, right? So notice that it would be 1 plus 1, which is larger than, it's going to be larger than this one because this is the small, it would have been either the same or smaller, right? Before that. Why? Because it was closer to the mouth of the blob, right? So that completes that next iteration of this while loop. So next we're going to figure out the next closest vertex to the blob's mouth. Remember, the blob is just bring it in my mouth, okay? Put it in my mouth. So it gets the one that's closest. So notice I have a 2 versus a 4 versus an infinity. So I picked the one with the 2. So to get there is this edge, right? That's the predecessor. So 4 is the predecessor or parent of vertex 3. And the blob will devour vertex. And then it goes on all the incident edges and say, hey, look, let's see, 2 plus 2 is 4. That's bigger than 0. 2 plus 3 is 5. That's bigger than 1, right? You notice those ones, it doesn't make much of a difference, really. Well, it doesn't make any difference, right? Then we have, because remember, they're already in the blob, so it means that their d values had to have been either the same or smaller. That's why we would never try to pick one of these edges to go back into the blob. It's always to the outside. So that's something I really want you to pay attention to. So versus 2 plus 4 is 6. That is less than infinity. So I'm going to update this. The d value of 5 to be 6 and its parent to be 3. And we've now considered all the incident edges, right? So next, let's go through and figure out which vertex goes in the blob's mouth? It's going to be the one that's closest, which is vertex 2, right? So to get to the orifice of the mouth is through this edge here, right? Because that's the parent of 2 is 1. So the blob devours vertex 2. And then at last, we check all the incident edges. So notice that I have 4 plus 3 is 7. That's bigger than 1. Don't do anything with that. And then next we have 1 plus 4 is 5. That's less than 6. So I'm going to update this. So I'm going to relax this edge. This one right here. Its parent's going to be updated to 2. And next, of course, we are going to pick our next one, right? I do have a question for you, just something to think about. Do you notice how when I was talking about this, I always told you that the D value either stays the same or goes smaller for any one that's already in the blob, right? Do you notice that doesn't matter at all, right? Because it will never pull that out of this priority queue, right? Because this is the vertices that are outside the blob. It's just a fun little detail I wanted to point out to you. So if you were to implement this using loops, like as opposed to a priority queue, just a classic one where you pick the one with the smallest D value, I must stress one implementation detail you have to be very careful about is that if you just pick the smallest D value, that isn't good enough. You're going to need to make sure that you mark umin, so you'll have a way of marking it like I mentioned earlier. So you have to pick the smallest one that isn't marked. So the ones that are marked are in the blob. So that's why we don't have that step in this version of Dijkstra's algorithm. But this is just an interesting observation to notice because of the way we always pick the vertices. It's always that the value of the vertices is D values. They always stay the same or go up. They never go down afterwards, right? It's always going to be some non-decreasing order for the D values. Because we always pick the one that is closest to the blob's mouth, right? Which is at the origin. So let's pick the last one here. So notice that I could just use this edge here. Because notice that the D value for 5, that's the last one we have left. There's the only one we have left. So by default, you would pick this one. You take that one. Blob devours this and has devoured the entire graph. And of course, you could go through all the incident edges again, perform relaxations, but you'll notice that none of them would get updated because, of course, it would be 5 plus 1 is 6, that's larger than that. 5 plus 4 is 9, that's bigger than 2, right? So notice that you wouldn't relax these edges. That's the thing I'm really getting at. So if we're talking about selection, the priority queue takes care of that for you. But the edge relaxations, we don't relax on edges that are already they're already in the blob, right? We wouldn't relax these again. That's what I'm getting at. So hopefully you can see that's rather interesting. Because it's going to come up a little later. So this all comes back, by the way, to the optimal substructure that we observed for the single source shortest path problem. And this is what actually will come up in the proof of correctness. But yeah, here's an example execution. The shortest path tree is, in fact, indicated with the red edges here. Yeah, that's Dijkstra's algorithm. So as a little exercise, I encourage you to try picking another source and seeing if you get a different shortest path tree. Or just simply try, just try another set of vertices. Just try another one. Just try a couple just to see if you can convince yourself that you understand this algorithm. But yeah, that's Dijkstra. So, are there any questions? Any questions at all? Don't be shy. I brought up a whole bunch of fun things in here, right? Remember, as long as you remember that you always pick the closest vertex to the source that's not in the blob yet, that's all you need. That's all you need to remember how you would carry out Dijkstra. The relaxations is the mechanism for which we update those distance values, the D values, at each one of the vertices whenever the blob devours the next vertex, okay? So, anyways, that's that. So now we've got ourselves our next thing we need to play around with. Namely, proving that our algorithm here, Dijkstra's algorithm, in fact, correctly computes the shortest path tree. So we're going to keep the algorithm right here for now. I'm going to erase this example here. But it's going to be important for us to be able to sit down and actually prove that the algorithm is correct. So let me just give me one moment here. I'm just going to kind of reorganize my thoughts here. Yeah, that's what I needed. So what we're going to do next is we're going to establish the correctness of Dijkstra's algorithm. So a lot of the intuition behind this comes from Prim's algorithm. So the way we would go about with Prim's, some of the mechanisms that we use all come out of this. So you're going to see that there's a couple of things that are kind of couple moving parts here. The first one is ensuring that we have a spanning tree, right? So once we know that Dijkstra's spitting out a spanning tree, we need to know that's the shortest path tree, right? So we need to come up, so we're going to have a valuable invariant that's going to, so remember, for those that aren't acquainted with the concept of an invariant, it means that when this specific condition happens, when this happens, you can guarantee that at that stage, that the algorithm is we're behaving exactly the way you would anticipate. So that if you carry out the full execution of the algorithm from start to finish, if this invariant is satisfied each time, that means that at the end of this process, it has to be that at the end, you end up with the whole thing being a shortest path tree. So I'm going to come up with an invariant for us that will give us such a thing. So that each time we bring a vertex into the blob, which we know this algorithm will go through all the vertices, because the priority queue contains all the vertices, and it will dequeue, or in particular, it will perform a removal of each one with the smallest key, which would be its D value, right? We want to get the one with the smallest D value. It will go through every one of the vertices, pulls them out, and I want to have it so that for sure, each time I take one out and I pull in and point it out to you, it has to be that the path from that vertex to the source is in fact the shortest S. And if, say, that vertex is called umin, it's S umin path. It has to be a shortest one. So that D value has to match up exactly with the shortest path length, or the true distance from S to that vertex. So we're going to be doing that now. So we're going to establish the correctness of Dijkstra's algorithm. And then after that, I'll have some remarks, and then we'll talk about why we assume that the edge weights are non-negative as opposed to them being allowed to be negative, and see what kind of nonsense we come up with. I'm just going to drink a little bit of water. But for anybody popping on in, I hope you're having a wonderful day. Okay, so let's get into this. Just want to make sure I have a good marker, because I would hate to have this when I'm just dealing with a silly marker. So let's see. That one's okay. That one's okay. Let's go with this. So anyways, we've seen Dijkstra's algorithm, we've seen an example. Now we actually have to prove the correctness of Dijkstra's algorithm. Now many of the key ingredients that prove the correctness of Dijkstra's algorithm, we actually have seen them before with Prim's algorithm. Just, we're going to need the right invariant to make this work though. So the first thing I have to do is convince you that this is actually going to be producing a spanning tree. The second thing is that whenever I introduce a vertex into the blob, that the path that I get by extending an edge to this vertex, the one for which the blob will use to devour that vertex, it has to be that that itself is a shortest path. Because remember, if it is in fact a spanning tree, there's a unique path from that vertex to the source. So that means it has to have a shortest path length. So I need to ensure that these two things are satisfied for the correctness of this algorithm to be the case, okay? Sorry, we need to ensure that these two things are in place for the correctness of Dijkstra. So first I gotta convince you that this algorithm does produce a spanning tree. So as with Prim's algorithm, Dijkstra's algorithm constructs a spanning tree T as it selects n-1 edges, where n is the number of vertices, implicitly. So previously I discussed how this edge would appear in my previous lesson about Dijkstra. Implicitly. And the algorithm always extends an edge in T, so meaning I bring in another edge that grows the tree in T from inside the blob to outside the blob. Creating no cycles. So there's going to be no cycles. So we know that we're going to end up at the end of the day with a spanning tree, just like in Prim's. It's just that the structure of the spanning tree we get isn't going to be a minimum spanning tree. We want to show that it's a shortest path spanning tree of the source S. So that's what I have to show you. So one thing I really want you to observe, so this is an important observation that's going to play a key role in the correctness of this, is that each vertex V in the set of vertices is DQ'd from the priority queue Q and joins the blob capital B. So we know that each one is going to be, leaves the priority queue and goes into the blob, right? So this is an important fact. So this is going to happen with all the vertices. So what I need to do is show you that each time when it joins the blob, that it has to be the case that when I extended that edge to this vertex that comes out of the priority queue and joins the blob, it's just hungry for that blob. It's just saying, hey, bring that one to my mouth, okay? It has to be that it is, in fact, the shortest distance from that vertex to the source, the orifice of the blob, okay? So just as a little bit of notation for us, for any pair of vertices, U and V in the set of vertices, we're going to call DUV is going to be the length of a shortest UV path, which we'll colloquially just call this the distance from U to V. So if ever I say the distance from u to v, it's always going to be the length of the shortest uv path. As a remark, just for the sake of completely defining this object for you, is if I write duv is equal to infinity, it just simply means there is no path. There is no uv path. That's what it means. So that brings us to a theorem that's going to be the one that we're going to use to prove the correctness of Dijkstra. So I'm just going to keep Dijkstra's algorithm up here. And now we have all the bits and pieces for this theorem. So we know we're going to end up with a spanning tree. And we know that each vertex is going to get dequeued from the priority queue and it joins the blob. So what happens when that vertex joins the blob? That's going to be the big thing that we need for the correctness of this algorithm. Now, this isn't the only way you could prove this. This is just one such way. So here's a theorem. In Dijkstra's algorithm, when vertex v of G joins the blob, when it joins the blob, it has to be that v dot d is equal to the distance from S to V. That is, v dot d is the length of a shortest path. Length of a shortest path from S to V. And we have computed a shortest SV path. That's the theorem that we're going to be proving. Again, we're going to be coming to our best friend, contradiction. And here's sort of the setup that we have. So we're going to consider when V joins the blob, and I would like to show you that it is in fact going to be the true shortest distance from S to V. What does it mean if that isn't the case? That means that there has to exist, so this has to be true for all the vertices, right? So that means that there is some vertex where this isn't satisfied. Recall that if it was the case that v dot d was less than this, that wouldn't make any sense because, one, Dijkstra's algorithm always picks the one that is closest to the source, the next closest vertex to the source. Likewise, to compute a shorter path than the shortest path, we get back to the same issue we had about, oh yeah, presuming that there is a shorter path than the shortest path. That just doesn't make any sense. So that means that the algorithm had to have picked and pulled a vertex into the blob where the distance from S to that vertex was actually larger than the shortest distance from S to V. So what I'm going to do is I'm going to show you a recipe for showing that if such a vertex existed, one for which this condition did not hold, that we're going to see that that vertex can't exist. And if anybody proposed one to you, that I could show you how you could swap it with this better one that would be a part of what the algorithm would actually do. So now that we have the game plan, let's get started. So assume otherwise. Then there is a vertex a vertex V such that V dot D is strictly bigger than the distance from S to V, right? Now, we want to figure out when this first happens. So I'm going to give this vertex V a name. So I'm going to say, hey, look, we're going to see where the first time this mismatch happens, when Dijkstra goes wrong in the hypothetical here, okay? So remember, we're assuming this such that we can derive a contradiction. So we're going to let Z be the first vertex, the algorithm pulled into the blob B such that so let Z be the first vertex the algorithm pulled into the blob B such that Z dot D is strictly bigger than the distance from S to Z. Very important. I want you to pick this up, put it behind your ear and say, I'm going to come back to this. I'll come back to this. So just remember this fact about Z. Remember this fact about Z. So just to be very clear with you. So it has to be that Z was the first incorrectly picked vertex by the algorithm, where when this algorithm selects this edge, it extends to Z. So it selects an edge to get to Z, but that doesn't result in a shortest SZ path. So it means that there has to be a different SZ path too, right? So graph G is connected. So there exists a shortest SZ path. I'm going to call this P in G. So it's going to be the shortest SZ path. So I'm going to draw us a fun picture. I must stress, the picture isn't the proof, but so here's S. There's Z. Imagine it goes on some, so this is path P here. And imagine that there's the blob. And I must stress that Dijkstra, the way the blob is formed, it need not be the case that all of this path is in the blob, right? If it was, then it would be a part of this path, right? But it isn't. This is a different path than the one that gets picked by the algorithm. So what we're going to do is we're going to consider the moment that the blob devours Z, meaning that it picked it. So I want you to keep in mind the situation here. So the algorithm is what's controlling the blob, right? However, this is the shortest SZ path. And it need not be the case. And keep in mind, it doesn't have to look exactly like this either. It's just the point is that there will be some vertex that's probably not in the blob, right? There's going to be at least one. So consider just when Z joins the blob B, and let Y be the first vertex in P, starting from from S to Z that is not in B. So we follow along this pathway and we find our first vertex that is not in the blob. This is Y. You might ask, Dan, does it matter that the vertex isn't in the blob? Yeah, it does. It does. That matters a lot, right? Because remember, the way Dijkstra's algorithm works is it picks a vertex to go into the blob because it had the smallest D value, right? So right now we have a scenario where it could have picked Y or it could have picked Z. So it's going to be important for our setup. Because remember, it's going to incorrectly pick Z. That's at least the presumption that we're making here from the way the argument is forming, okay? So we're going to let X be the predecessor of Y in P. So for the sake of our algorithm over here, this means that Y is equal to the parent of X in the spanning tree that we have. So that's what Y is in relation to X. So X is over here. Y is outside the blob. And it must be, this is the case at that time. It's at that time that this is the case. Now, I explicitly drew X right here. Why is X in the blob? Well, it's by construction, right? Because I told you that Y is the first vertex in P, starting from S to Z, that is not in the blob, right? So it means the one that precedes it in the path has to be in the blob. So observe, by construction, X is in the blob. Likewise, remember that Z is the first incorrectly picked vertex, right? But remember, X is in the blob, right? X is in the blob. So it means that Dijkstra had to have picked correctly such that if I look at the D value of X, it had to have matched the shortest path distance, right? That's what it means. Since Z is the first incorrectly picked vertex, it must be that X dot D, so if I look at the D value for X, it has to be exactly equal to the distance from S to X. This is very important for the setup of this. But yeah, so now we're going to see what we could do with that information. So just remember that it's that at the moment that Z is brought into the blob, it has to be that its D value is strictly bigger than the distance from S to Z. That's what it means to be incorrectly picked. I'm gonna fix my X here. Okay. Now we know that x dot d is equal to the distance from S to x, right? When x joined the blob, blob B, regardless if an edge relaxation occurs or not, for vertex y. That means I'm relaxing the edge or I'm not, to y. At that time, it has to be the following. At that time, y dot d has to be less than or equal to x dot d plus the weight from x to y. But what's this? What's this? Well, x dot d is just the distance from S to x, right? And I'm just going to keep this, the weight from x to y. I'm just simplifying it a little bit. Since I know this, I'm just going to put that in there. Now, notice that y is next on the path P from x. Then it has to be what? What has to be true about y dot d then? Y dot d has to be, if this is the case, y dot d is in fact the distance from S to y. But here's the catch. Remember back to what I just drew over here. Remember that z is the one that first gets incorrectly picked. Y isn't in the blob, so the algorithm chooses z instead of y. So what does that mean about the d value of z versus the d value of y? It always picks the smallest d value, right? That's what Dijkstra's algorithm over here does. The one that isn't in the blob with the smallest d value. However, z joins the blob B before y. Which means what? What does it mean about their d values under this assumption? It's z dot d has to be less than or equal to y dot d, right? That has to be true because I pick z first. I pick it before y. So that's an important thing to observe about Dijkstra's algorithm. We always pick the one that has a smaller d value. Now this is where we're going to bring up a property that we had before from earlier, where we showed that if I give you a shortest, say, ST path, that if I look at a subpath in the shortest ST path, that subpath also has to be a shortest one with respect to its ends. So we're going to use that property now. I mentioned it was a key ingredient. This is where we're going to use it. Vertex, sorry, it just looks like it's melting a little bit. Now, vertex y is along the shortest SZ path. Remember, it's right here. So I have x, y here, and then z's over there, right? So it's along this shortest path. So that means I should be able to decompose the path. So I have a subpath. So watch this. So by our lemma, remember that's the one that says that a subpath of a shortest path is also a shortest path. So by our lemma, the distance from S to Y plus the distance from Y to Z is equal to the distance from S to Z. So I'm going to use two ingredients here. I'm going to star this first one here, the one that says Z dot D is less or equal to Y dot D, and I'm going to double star this one. Now, this is where the part about the edge weights being non-negative is going to be critical in this proof. Since all the edge weights of G are non-negative, for those that are more formally inclined, that means that if I give you an edge E, the weight of that edge is greater or equal to 0. It has to be, since they're all non-negative, remember that means that the distance I travel either stays put or I move forwards. I never go backwards. That means the distance from Y to Z, so if I were to go from Y to Z, it has to be greater or equal to 0, right? If I wanted to go from here to there, it has to be greater or equal to 0, right? It doesn't go backwards or something like that. The edge weights are 0 or greater. So combining star and double star, here's what we get. Z dot D is indeed less than or equal to Y dot D, right? That's what that says over there. Now, we know that Y dot D equals the distance from S to Y. But what's this less, like, can I find something that bounds this nicely? Well, surely the distance from S to Y will, because it's equal to it. But remember, the distance from Y to Z, if I want to go from Y to Z, it's going to be along this path P, right? It's going to be along that path. And it's non-negative. So it means it's either going to make this value, if I added in the distance from Y to Z, it's always going to make it the same value or larger, right? But what's this? The distance from S to Y, then plus the distance from Y to Z. What is that? Remember, these are two subpaths. I've combined them into one longer path. That is, they're going to be the distance of, it's the distance of P, right? It's the distance from S to Z, though. So for those that remember, pull out the thing that you had behind your ear. Pull it out. Pull it out. What did we say before? We said Z dot D is greater than the distance from S to Z, right? But this says that the distance, so Z dot D is less than or equal to the distance from S to Z. Therefore, both Z dot D is greater than the distance from S to Z, and Z dot D is less than or equal to the distance from S to Z, yielding a contradiction. Z can't exist. You can't have both those two things simultaneously. So such a Z can't exist, because it would have to be that it's both that its distance is larger, its D value is larger than the shortest distance, but it's also less than or equal to the shortest distance. So you might look at this and say, Dan, what does this proof mean? So it means that if you had a mismatch between the two, I could show you how it would make a bunch of nonsense, right? So you could go through conceivably this process over and over again, and you'll notice that the one it always picks is the one that is closest to the source every single time. That's what Dijkstra's does. So from this, since we know we're producing a spanning tree, And every single time from our observation, when we take out a vertex from the priority queue, it joins the blob. The theorem says that when we do this, the d value it has, using the edge that we extend to this given vertex, when it joins the blob, its d value matches the distance from S to that vertex. So as a corollary to all of this, we get the correctness of the algorithm. Meaning that it solves the single source shortest path problem. So let's write that out now. So for those that have never heard of a corollary before, it's just simply, it's a theorem that follows from previous theorems. So usually their proofs are rather straightforward. They follow from the major results that you have. So that theorem did all the heavy lifting for this from the observation I gave you earlier. So the corollary is given a weighted connected undirected graph, G is equal to VE, where the weight of E is greater or equal to 0, where it's non-negative, for all edges. Dijkstra's algorithm produces a shortest path tree of S. So this is how this is one way to establish the correctness of Dijkstra's algorithm. And it all boils down to the key idea that we had from before, is that we have a very lazy blob. Just brewed to my mouth. So are there any questions? Any questions at all? I know today is a rather quiet day here. Thought I would go through a nice classic here with everybody. But yeah, that's Dijkstra's algorithm. So I thought I would go through a few remarks with you before we get into the last thing I wanted to talk about here today. Well, we got ourselves like about an hour, so we'll see how we're doing here. Well, keep in mind, if you have any questions, I'm happy to answer those. It looks like we have some time for that. I thought I would make a few remarks. The first one is that we know how Dijkstra's algorithm correctly operates for when we have non-negative edge weights, right? Well, what if we wanted to have negative edge weights? So let's talk a little bit about this. Dijkstra isn't the only algorithm in town for solving single source shortest path problem. It does for non-negative edge weights. As we're going to talk about, I'm going to show you how it isn't going to be the case that you're going to find one of these shortest path trees. The shortest path tree, as we've defined it, won't exist sometimes. And naturally, that also tells you how Dijkstra won't work. So I'm just going to mention a few remarks with us. Let's talk about some remarks here. So if ever you want to have it where you consider when there's negative edge weights, there does exist the algorithm of Bellman and Ford. So I'll say other algorithms exist, such as the algorithm of Bellman and Ford. So the algorithm of Bellman and Ford, it runs in big O of n times n time, which this is just, I can rewrite this as big O of n cubed. It's slower than Dijkstra's algorithm, but it has a fun property to it, is that it does work with negative edge weights when they're present, except in the presence of what is called a negative weight cycle. That means that there exists a cycle such that when you add up the edge weights in that cycle, that they sum up to a negative number. That means that you can't have a path unless you're just strictly looking for simple paths. If you're looking for just a path or walk, it means you could just keep, as soon as you encounter this cycle, all you do is go over to the cycle and you keep walking around the cycle over and over and over again. And you can keep making shorter and shorter and shorter paths, which means that there is no optimal solution in these cases. So if you're interested in non-simple paths, Bellman and Ford will be able to detect these situations when you run into one of these negative weight cycles in the graph. Because all you need is one of them to exist in your graph, and there is no optimal solution in these cases. If you require it's a simple path, you're just out of luck. Solving the single source shortest simple path problem, where you're trying to find a simple path, when you introduce negative weights like this, it changes the problem quite a bit. The problem actually becomes much harder. So this works. And I must stress again, if you're just looking for a walk in the graph, this is good enough for what you're looking for. If you're looking for a simple path, you're just out of luck with Bellman and Ford. In the presence of one of these, the problem becomes much harder. If you could solve it, you could solve some pretty nasty problems out there that require exponential time. As far as we know, we don't know. But the best out algorithms we have for those types of problems, or where we try to compute just generally, regardless if the weights are negative, positive, or zero, in that broader problem, computing a simple path in that case is much harder. It's much harder to do. Computing simple shortest paths is much harder when negative weights exist. So if you try to compute the shortest path, or shortest simple path, if you try using Bellman Ford, it'll just give up. There's no luck. You're not going to find it. However, this comes back to something I told you about a little earlier on, that in the situation of Dijkstra's algorithm, it doesn't matter if the path is simple or not. The optimal solution will consist of simple paths. However, when you introduce negative weights like this, that delineation starts going away. So notice that here, if you just want to find a path, in that case, when you have a negative weight cycle, there is no optimal solution here, because you can just keep walking around the cycle over and over again forever. There is no optimal in this case. However, here, you can't use an algorithm like this to give you the shortest simple path. Hopefully that's clear. If you're wondering about what Bellman and Ford is about, I'm not going to talk about Bellman and Ford here today, but the way it works is actually it uses the same mechanism, the edge relaxation. Except what you do is you relax on every edge. So you go through every one of the edges. So you're just going to go through for each vertex, you're going to relax on each one of their edges that are incident on them in a very specific way. I'm not going to go into those details here, but that's very naturally why the running time looks like this. You're going to relax on every one of the edges at some point. But you're going to do this for a certain number of rounds. You're going to do it in terms of, you're going to do it, I believe it's n-1 if my memory serves me correctly. Yeah, you're going to do that many rounds. On each round, you're going to relax all the edges. And that's how Bellman and Ford works. It uses the same mechanism we had for Dijkstra. Dijkstra, we could do it a little bit more intelligently because of that assumption over there. So there's a couple fun remarks. So I thought next we'll talk about... I would talk about this issue around negative edge weights when it comes to Dijkstra's algorithm. Okay, so the next thing I would like to talk about is why doesn't Dijkstra's algorithm work with negative edge weights? So let me just pose that here. So let's answer this question. So why does Dijkstra fail for negative edge weights? So classically, the single source shortest path problem is defined where the edge weights are non-negative or positive. But let's consider the broader case when the edge weights are allowed to take on a negative value. So why is it that Dijkstra's algorithm isn't capable of handling this situation more broadly? Well, I'm going to consider a basic counterexample. This is a very simple counterexample. We're going to have the source S here. We're going to have a vertex U and a vertex V. What we're going to do is I'm going to make a constant C. It's going to be greater than 0. And I'm going to assign the edge weights like this. So I want to first, before I get too crazy with this, I'm going to assign these to be C, C plus 1, and say C plus 1. So I'm just going to keep all of them right now positive because C is greater than 0. So if you were to use Dijkstra's algorithm here, what would happen? Well, it would begin by doing what? Well, it'll pick this edge to extend for the shortest path tree, right? And the blob would consist of S and U. And then it'll update the distance from here to there potentially. No, does it relax this edge? This one? No, because it'd be C plus 1, which is larger than C plus 1. So in this situation, you would have it where the next time around, the blob would devour this vertex V, and it would do it by this edge. And you would end up with the shortest path tree, right? But notice that when I first selected U, I did this because this was the least weight edge and then it's going from S to U, which happens to be the shortest distance from S to U. Well, whenever we worked with Dijkstra's algorithm, we always we either stay put or we move forwards, right? That's the underlying assumption that is made when we use Dijkstra's algorithm. So let's make this a little bit more funky. Let's change this edge weight from C plus 1 to be minus C plus 1. So, is it still true that SU, the path SU, is in fact the shortest SU path? Well, look at it. Well, let's see. We have this other path here, C plus 1 plus minus C plus 1, or negative C plus 1. What's this? That's 0, right? That's strictly less than C. So this is actually not computing the shortest path from S to U, which if you go back to our proof of correctness, the part in our stage in our proof relied on this fact that all the edge weights were non-negative, right? This is why. Because what happens is I could potentially have it where when I commit from S to U, it was because that in fact was the shortest distance from S to U at that time. However, that doesn't mean that later on I could potentially take back the distance that I could have traveled by using another route. Because remember, we either stay put or we move forwards. So the actual shortest path from S to U is actually this one right here. But this is where it gets even stranger. That's assuming it's a simple path, right? So if I wanted to compute the shortest simple path from S to V, I would go from S to U to V, right? However, if I wanted to compute a simple path, just presume that's the case. Presume I wanted that. Which is what Dijkstra would do, by the way, in this case. It would actually extend another pathway off over here, right? So he would say, hey, look, if I relax, would I relax on this edge? Yeah, in this case I would, because C plus negative C plus 1, that is less than 0, right? That would be negative 1, which is less than C plus 1, so it would relax and then it would use this. And that would be the supposed shortest path tree that it computes, which this isn't going to cut it, right? Because notice that this does not contain the shortest path from S to U. That's not right. In fact, in this case, if I wanted to compute the simple paths from S to U and the simple path from S to V, each their own shortest versions of them, if I take the union of their edges, it's not quite clear if that's going to end up being a tree anymore. Do you see that? So notice that the shortest path from S to V is this way, right? The shortest path from S to U is this way. If you take the union of those edges, and keep in mind, those are the only shortest paths. There aren't other ones. It forms a cycle. It doesn't form a tree anymore. So there does not exist a shortest path tree here. In fact, it's even worse than that. That's presuming you were looking for a simple path. If you wanted just a path, notice that if I were to just get anywhere near here, notice that I could just go back and forth from U to V like this. Back and forth, back and forth, back and forth, creating an ever increasingly negative path. And I could just stop whenever I wanted to, but if I do, I'll miss out on an even better path. Meaning that in these situations, when there exists a way to go back and forth like this, which is something that a non-simple paths are capable of doing, because it's just a walk, right? I could go back and forth over and over again. That's sufficient to say, hey, look, there is no shortest path tree in this case. In fact, there does not exist a shortest path. But yeah, that's why Dijkstra's algorithm fails for negative edge weights on undirected graphs. So regardless if you're looking for a simple path or a non-simple path, or just a walk, such a counterexample, or technically this is an infinite set of counterexamples, is enough to tell you that Dijkstra's won't cut it. Hope you thought that was pretty interesting. Yeah, or any questions? Any questions? Don't be shy. Don't be shy if you have any questions. But yeah, you'll notice here that this is exactly what you would expect to happen with Dijkstra, because once you commit the vertex U, you're at the mercy of however the rest of the tree is, okay? And the issue here is that that edge right there is along a shortest path. The minute you have that, you're screwed from the perspective of Dijkstra's algorithm, at least. But yeah, that's Dijkstra's algorithm. Hopefully you thought that was pretty interesting. We've seen how we could solve the single source shortest path problem. But yeah, are there any questions? I'm happy to invite any questions. So if you have any questions at all, I'm happy to answer them. The blob was trying to escape the container a little earlier, so I'm going to try to Try to contain that. There we go. I got the lid on. So, any questions at all? Don't be shy. Don't be shy. Just gonna go check on things just to make sure there's nothing strange. I'm just gonna check on things here. We're getting some weird noises. That was some strange stuff. I think it's one of my USB ports. But no, if there aren't any other questions, I think this is a great place for me to stop, if that's the case. I've covered everything that I planned to cover. Sorry, I'm just dying from from all the excitement. I'm actually kind of surprised we actually finished early, of all things. See, that's why I'm dying. It's because I just live off of this stuff. But yeah, no, so if we're all done here, I'm going to stop right now. I want to say thank you so much for coming on out. It was a pleasure to have you all down. And have yourself a beautiful day. I'll see you later.